pretty awful. So, did you check?
Hello, I'm Katia Cardoso. Welcome to the European Space Research and Technology Center in the Netherlands. This is the largest European space agency establishment, and here, in the heart of the Netherlands, many of the space missions that are built in Europe start and develop. Today, we are joined virtually on your side by many moon explorers that are participating in the MoonCamp Challenge, a European educational project with a partnership of ESA, Airbus Foundation, and Autodesk. Today, we'll all learn about the future of exploration, and I'm joined by an expert from the Human Robotics Exploration the Directorate from ESA, which will present us an overview of the past and future lunar exploration missions. Welcome, James Carpenter.
So, good morning, good afternoon, good evening, wherever you are. So also, I'd like to welcome you to ESTEC here in the heart of the Netherlands. It's my absolute pleasure to spend a bit of time today talking to you about the past and the future of space exploration, focusing a little bit on the moon, and hopefully give you some idea of some very exciting things that I think you're going to see in the coming years. So to start with, you'll see on your screens a survey which we're taking right now using something called Mentimeter, and you can join in this survey. So if you go to, what is that? Oh, it's gone. So if you could go to menti.com and you can use the code, which is 747225, and you can join in this survey. We're asking you the question, what is exploration? And what you'll see already is that there is not a common idea of what exploration is. Exploration is something which is deeply personal. For some, it's science. For some, it's technology. For some, it's exploring the unknown. For some, it is going to places that are incredible and unimaginable and places that are new. For some, it is about coming together as humanity to do extraordinary things. Now, we in ESA have lots and lots of different countries working together to explore space, and it's our job to work with all of these countries to help them meet what they want to do what they want to achieve. And each different countries and different people from around the world with different cultures have different ideas of what exploration is. And so because exploration is such a deeply personal and individual thing, coming together and doing exploration as a group is something which is it's quite tricky, but it's also wonderful because it brings together so many different ideas and different approaches. So we're going to leave this on throughout the talk. We'll come back to it later on, and we'll get some idea about how you've all voted. So if we go to the next, actually, if I just try this, does that work? Hold on, wait a second. Okay, I'm going to ask you to change the slides for me. Thank you. Okay, let's go to the next slide. And again, thank you. So I would like to start our adventure together today with Apollo. So Apollo was an extraordinary program. Over less than 10 years, went from almost a standing start to putting human beings on the moon. This is the first and the only time in history that human beings have ever set foot on another planetary body. And we also now know that even though this was not driven by scientific objectives, by the quest for scientific knowledge, this was an incredibly important mission for science. The science that came from Apollo and the samples that came back from Apollo, which are still being studied in laboratories today, have formed the basis for almost the whole of planetary science. They've told us about our own planet, the origins and the history of our own planet, and about all of the other planets. And so to start with, we're going to explore a little bit about what we know about the solar system, and about the Earth, and about the Earth-Moon system, and our shared history as a result of these first samples. So the first thing we think we know is that the Earth and the Moon formed together during a very violent event. So in the very, very early history of the Earth, there was a massive impact from an object about the size of Mars, which is often called Theia. And this object slammed into the early Earth, kicked up huge amounts of dust and gas, and these went up around into orbit around the Earth. And over time, they came together, accreting together to form this ball, this globe, which we now know as the Moon. And we know this from the rocks that came back from Apollo, which when they're studied, look very, very much like terrestrial rocks. They look like the rocks that we have on the Earth chemically, with some key differences, but enough that we are fairly confident they must have come from Earth. However, if we model, we try and understand using the physics of how this thing should have come together, we see that we ought to see traces of this body, this Theia that slammed into the early Earth, and yet we don't really see them. They're not obvious in the rocks that we get back from the Moon. And so the question is, where is Theia? Where are these traces of Theia that we ought to be seeing there? And so even though we have a good understanding, we think, of where the Earth and the Moon should have come from and how they've shared their past, there are still some big questions which remain to be answered. So moving on, if you start the film, we have a short film produced by some colleagues working in NASA at the Goddard Space Flight Center in the USA, showing you a brief history of the Moon and what came about and how things we know. So after this early Moon was formed following this giant impact, it became very, very hot and molten, something called the magma ocean. And as this magma ocean started to cool, crystals started to form of minerals. And light minerals, using calcium and aluminium, these floated to the surface. And these formed these light areas that you see today. And then this happened. This was a massive impact, the formation of the largest impact crater we found in the solar system, called the South Pole Aitken Basin. And this impact, we believe, marks the start of a period where very, very large impactors were raining down onto the Moon and the inner solar system, creating what we call the basins, these very, very large impact features, very large craters that we see on the Moon now. And after these basins were formed, volcanism started to occur. So material from deep within the Moon started to erupt up onto the surface, and with it, it brought heavier metals, things like iron and titanium and other heavier things, from deep within the interior of the Moon up onto the surface. And this volcanism, this flooded volcanic material, makes the dark areas that we see on the Moon today, what we call the mare. So then we move into a period where cratering continues. So at a much smaller things than the impact basins that came earlier, but a continuous raining down to the surface. And this churns up the surface, creating the rugged and scarred landscape that we see today. The mountains and the craters all across the Moon. And of course, the areas that are much older, before this mare volcanism, are much more cratered. And the areas where we have the volcanism, because they're younger, are less cratered because they've been hit less often. And then we move into the recent history, so the last billion years or so. And then we still have craters, but in these craters, the material that they threw out up onto the surface has been there for less time. It's been exposed to space for less time, and so it remains very pale, hasn't darkened like some of the other things, and it creates these rayed craters that we see on the surface today. And that, in a nutshell, is the history of the Moon as we see it today. So the Moon, and what's really important about all of this is not just it's about the creation of the Moon. Everything that you saw there, these massive impacts and things like that, those also happened on Earth. The thing is, Earth has plate tectonics, it has wind, it has weather, rain, water, and these things will tend over time to erode the surface. They destroy the geological record of this ancient history. This is very important because if we don't understand the formation and the history, the early evolution of the Earth, then we need access to these kinds of rocks. Also, this period of bombardment, when these massive things were raining down onto the surface of the Moon, they were raining down on the surface of the Earth too. And it just so happens that these events, this large impact period, coincides with the earliest observed traces of life that we have found on Earth. And so there may be that there is some relationship between life's emergence on Earth and this impact environment, the context in the solar system at the time when these events happened. So we think we know, for example, now that the water that we find on the surface of the Earth, in the oceans and in the rivers and in the atmosphere, did not come from the early Earth. It looks like this was probably delivered by asteroids and comets and meteoroids impacting onto the surface of the early Earth. And so the Earth, life on Earth, the chemistry that enables life on Earth is related intimately with what is in space. And so going to the moon can help us to understand this better. Well, one thing people have talked about for a long time is the idea that there would be meteorites from the early Earth on the surface of the moon. This is talked about for a long time. We find meteorites from the moon on Earth that have been thrown up off the lunar surface by impacts. So they must be impacts or meteorites from the early Earth or from the Earth on the surface of the moon too. And actually a couple of weeks ago, for the first time, a meteorite, a rock that was brought back during the Apollo era, was tested and was found to be very, very similar to minerals that we find on Earth in Earth's earliest rocks. And it's very difficult to understand how that could have formed on the moon given the conditions there. And so one possibility is that we have found the earliest ever rock observed from Earth on the surface of the moon. So this could be the beginning of a very exciting future science of examining the early Earth through rocks that we find on the moon. So the moon has not just been a witness plate to the Earth, it has witnessed the whole of solar system history. So because the moon is very ancient, but has had this volcanism, it has been exposed to the sun. Material thrown out by the sun over billions of years has been hit the surface of the moon. And the sun, of course, has changed over that time. And we don't really know how the sun has changed during its history, but throughout its history, it's been raining down material onto the surface of the moon, and that would have been trapped there. So these would have been elements and atoms thrown out from the sun in what's called the solar wind. At the same time, the moon has been sitting in the solar system, and the solar system has been moving through the galaxy. So in that time, the solar system would have passed through clouds of dust and gas. It would have passed near other stars, near supernovae and other things. And the material thrown out by these things, or material in the galaxy that the solar system has passed through, will have moved through the solar system and will also have been trapped, have been captured on the lunar surface. So the image you see behind you are pictures taken on the right. You see a picture taken by Apollo astronauts at the lunar surface, and on the left, a picture taken from orbit by the Lunar Reconnaissance Orbiter, which is a NASA mission which is going around the moon in orbit now. And what you're seeing are layers of material, and these layers are regolith, which is this ground up dust and rocky material that's formed over time by these impacts. And this is formed, and then an eruption happens, and the eruption covers over this regolith, and a new regolith is formed, which is exposed to the dust and the gas that are coming from the sun and the galaxy for a period of time. And then another volcanic event covers it up, and then another, and then another, and then another. So over time, what you get is a time-resolved trapping of discrete periods of solar system and cosmic history trapped in these layers beneath the surface of the moon. And these are things that in the future we could go back to drill, to examine, to test and measure, to understand the history of the solar system and of the cosmos in ways that have never been explored before. So as well as examining the moon, we can also use it to understand the history of the Earth, the history of the cosmos. But we can also use it as a platform for which to look out into space. So what you see in the little green area here, this is a part of a radio telescope called LOFAR. So LOFAR is the low frequency array. It looks at very, very long wavelength radio from deep space, deep cosmic sources. Actually, this is one part of LOFAR. It's here in the Netherlands. But LOFAR is a telescope with parts here all over Europe. So which are all joined together in complex ways to create a telescope the size of a continent. Now, this telescope looks at long wavelength radio, and this is really important, long wavelength radio, because if you want to go to understand a particular part of cosmic history when the first cosmic structures were being formed a few million years after the Big Bang, if you want to look at this period of history, you can only do it by looking in this long wavelength radio domain. However, long wavelength radio in the wavelengths we want is absorbed but is absorbed by the Earth's atmosphere. In addition, the Earth is very noisy in these wavelengths, and so for the community that work in long wavelength radio astronomy, the next place where they would like to put a radio telescope is on the far side of the moon. The reason being, the only place in the solar system where you have both escaped from Earth's atmosphere and you can't see the Earth and the noise that comes from the Earth is the far side of the moon. And so the moon is a place also where we can go to observe the cosmos, and long wavelength radio is one great example of how that can be done. So these are different ways that we might want to use the surface of the moon in the future to perform scientific research, both of the moon, on the moon, and from the moon. And so let's look at a bit of the history of lunar exploration and how we know all of these things. So during the Apollo era, of course, this was an extraordinary era for space exploration. The Apollo missions from the USA, and you had the lunar missions, which were robotic missions from the Soviet Union. So this came to an end. The geopolitical reasons and the reasons why this was important for the countries that were doing it became less so. And so these programs wound up and came to an end. There was a long period of several decades where nothing went to the moon. Then, in the 1990s and early 2000s, we started to see new missions going back to the moon. So there was the Smart 1 mission from Europe, from ESA. There was also the Clementine mission, which is actually from the USA, but was not a NASA mission. In fact, that was a Department of Defense, a US Air Force mission. And that was repurposing spacecraft that had been developed for the what's called the Strategic Defense Initiative, or Star Wars, to look for nuclear signals or signatures of nuclear activity on Earth, was retasked to go to the moon and perform the first kind of real survey, chemical survey of the lunar surface from orbit. We also had the Hiten mission, which was from Japan, and then later the Lunar Prospector mission from NASA, which looked at the chemistry of the lunar surface and mineralogy of the lunar surface, and started to look for things like chemical traces of water, ice at the surface. We'll talk a bit more about that a little later. So then, as we move into the present times, from the 2007 through to 2015, we have missions like the Kagoya mission from the China, L-Cross, which was the mission which smashed into a crater in the polar regions of the moon, which are very, very cold and threw out dust and ice, water vapor. It was the first time water had been measured at the surface. We also had the Artemis mission, which is there now, which is looking at the relationship between the Earth and the Moon and the solar wind, the interactions between basically our Earth-Moon system and our parent star. The LADEE mission looked at the dust and things around the Moon. And then the first mission back to the lunar surface from China, Chang'e 3, which is in 2015, which in this year has been followed up by Chang'e 4, which is the first mission ever to land on the lunar far side. Later on this year, we'll see another mission from China, the Chang'e 5 mission, which will be the first sample return mission since the Lunar 24 in the 1970s. We expect to see an Israeli lander mission, which we expect to launch later this month. And so there's going to be 4 missions to the surface of the moon just this year. One of the important things we're starting to see are the emergence of new players in space. So missions from new countries who haven't been involved in lunar exploration and space exploration historically. We also started the emergence of the private sector, so missions that are being run not by countries, but by companies and by other entities that are non-governmental. And so some are calling this the democratization of space exploration. But what we are definitely seeing is an expansion which we expect to grow into the future. And within this, of course, ESA is working on some projects with international partners, and I'll talk a bit more about those in a moment. So all of these new missions have had an effect. And just to show you that, I don't know how well you can see this from where you are in the screen behind me, but this is a picture taken by the Lunar Reconnaissance Orbiter of the Apollo 14 landing site. And what you can see just over my shoulder is the Antares descent stage, the descent stage that took the astronauts down to the lunar surface. The ascent stage, which took the astronauts away, of course, is not there anymore. On the other side of the image, you will see ALSEP. ALSEP was an experimental package that the astronauts carried out of the lander and deployed onto the lunar surface. And this was a geophysical package with measurements to look at seismology, look at the lunar interior, and other things like that. And in between, what you see are these black streaks running backwards and forwards. These are astronaut footprints. So what we actually have now are images of the lunar surface from orbit around the moon, which are so good that we can resolve astronaut footprints at the surface. Now, that's just an example of the kind of data that we have now, the kind of things that have been possible through these orbital missions and these new technologies which have been sent to the moon as part of this new renaissance of lunar exploration, which we think is beginning. So that's the images, but here's some of my favorite science that has come as part of this. So this is a map that was made of the moon by the Clementine mission, looking at gamma rays emitted from the surface. And this is a map of thorium. So thorium is an element which doesn't combine with minerals very easily. It's something which we tend to find in the deep interior of the moon. And it's also an emitter of gamma rays. And so by mapping gamma rays from the surface from orbit, you can see where thorium is. And what you see is the area on the near side. There's an area on the near side here, which is the green area you'll see. And this is an area which is very rich in thorium. This is where this come up from the deep interior following some kind of eruption, magmatic eruptions that you have seen. The areas around most of the rest of the moon are purple. That means that there is very low thorium. These are things where there has been less volcanism. On the other side, just around here, over my right shoulder, is an area called the South Pole Aitken Basin. You'll recall from the video I showed, this is where this massive impact took place, which blew this massive crater, what we call an impact basin. And what you're seeing here are, again, traces of thorium. But this is not so much magmatism, this is not so much volcanism that's taken place. This is where we've actually stripped off the outer crust of the moon. And you're looking into the interior structure of the moon, things that are beneath the surface, and where eruptions have taken place, perhaps as a result of this big stripping away of the outer crust. So an important thing to note here is that all of the missions that went to the lunar surface during Apollo and Lunar, so all of the samples that we've retrieved come from this area on the near side, which is, you see high in thorium here. And these areas are exotic. They contain something called creep. And creep is potassium, rare earth elements, and phosphor. Now, this is exotic material that's been brought up from the deep interior. And we find traces of this in all of the samples that have come back from Apollo. So what we now know, based on orbital data like this, is that all of the samples that came from Apollo that we have used to create the basis of our understanding of the history of the Earth and Moon, or to understand the formation and history of planets in the solar system, something which has been the basis for planetary science, they all come from a region that is not representative of the moon. And so if we want to really understand all of these things, we have to go back there, and we have to get new samples from places that are new and unexplored today. Another major result I think is very exciting over the last few years has been the discovery or the confirmation of the presence of water ice at the surface of the moon. This is actually a very old idea. I think the earliest scientific paper that I have seen that makes any kind of reference to this is actually a French paper from Nature in 1892. It's a very old idea, but really was resurrected as an idea in the late 1960s. People realized that at the poles of the moon, where the sun moves around you like this, if you're sitting down a hole somewhere, it's possible that you would never ever see the sun. And so in these holes, in these craters that never see the sun, it would get very, very cold, and you could trap ice for very, very long periods of time. So this was talked about for a long time. It was really only with Lunar Prospector and Clementine that the first measurements that alluded to the presence of this were made. More recently, the Lunar Reconnaissance Orbiter has produced maps of the temperature at the surface. And this, combined with data from neutrons emitted from the surface, which you can use to find out where hydrogen is, and hydrogen is an important part of water, we can detect now where we think the water would be. And so we see that, and this is what you see on my shoulder is a map of where water ice could be stable for very, very long periods of geological history based on the temperature that's been measured there from orbit. Now, the pale blue areas are permanently dark. They never see sunlight. They're some of the coldest places in the solar system. The sun as low as 30 Kelvin and less. So that's minus 240 odd degrees centigrade. And the other areas that are darker blue, these are areas which do see some sunlight, but where just beneath the surface, within 1 meter of the surface, it could be cold enough to trap water ice. Now, water is very important because it's firstly, it can be a record of the sources of this water. So that could be the asteroids and comets and things impacting into the surface that have led to this water there. It could be water that's been formed through interactions between the solar wind and the surface, where the protons from the sun strike the surface, reduce the surface by pulling out the oxygen atoms in the minerals there and creating water, which then moves to the poles where we find them here. Water, of course, is also useful for humans. We can drink it. It's also hydrogen and oxygen, which is oxygen which we breathe, and hydrogen and oxygen together are rocket fuel. So it could be that here at the surface of the moon, at the poles of the moon, we have a resource that we could use as the basis for exploring the solar system beyond the moon. So this could, again, could be something that's very important both scientifically but also for the future of exploration. But water is not the only resource. We also know that across the lunar surface, have this regolith I talked about earlier, this ground up material, and this is made out of the minerals that exist at the surface, which have been ground down over billions of years of impacts. And these materials, we know, contain about 40% oxygen, and the rest of it is metals. So here you see an astronaut footprint. It is very, very fine-grained. It's been described as evil talcum powder. Okay, it's very, very fine-grained stuff, but it jumps around. It's very, very difficult to handle. But if you could take this evil talcum powder and you could pull the oxygen out of it, that oxygen could be used for propellant, for rocket fuel, and it could be used to support human explorers. And what you're left with are metals and silicon, things that you can use to make stuff. So conceivably, you could have a situation in the future where you're going to the lunar surface, you're using the materials you find at the lunar surface to create the rocket fuel that you need, the consumables for life support systems that you need, and the materials that you need to manufacture what you need to live and work on the moon and beyond in space. And so the moon can become the place where we as a species learn what it means to live and work off the Earth in a sustainable and sustained way. And in doing so, we can learn how to live more sustainably on Earth and how to be better custodians of the materials that we find here and the way we use those in our lives on Earth. And so we said earlier on that there were a lot of missions coming, and there's a lot of opportunities to come. And so what I'd like to talk a little bit about now are some of the ways that we in ESA are planning to work in this new environment, in this new democratized space exploration scenario that is coming, and the things that we're planning to do. So the first thing we'd like to do is to be able to respond to what we call missions of opportunity. So what you see over my shoulder, I suspect you can't read this very well from where you are, but what this does is to give you an idea of the scale of what is planned over the next few years in terms of lunar missions. So this year, in 2019, we will see at least 4 lunar lander missions, we think, from different countries. So on the right-hand side, or on your left-hand side, we have institutional missions. So these are missions that are planned, that are led by space agencies. So we have missions to the surface from multiple different countries, missions to orbit, and the creation of something called the Gateway that I'll talk about in a minute. On the other side, we have what we call commercial missions. So these are missions that are driven not by agencies, but by private sector actors, by private companies and others who are not necessarily related to the government, but maybe selling flights as services to governments and to national users. And so we're looking to see how can we partner with some of these people, with private sector and public sector, to get to the surface and to take Europe into space, into the moon. So one of the ways we're doing that is by partnering with commercial enterprise. So we are building partnerships with companies in Europe who are planning to go to the moon. So those could be companies that are developing landers and would like to fly to the surface using landers. So there's a company called Part-Time Scientists in Europe who are planning to build a lander to go to the lunar surface in the next couple of years. There are also companies looking to build services. So Surrey Satellite Technology in the UK, working with a company called Goonhilly Earth Station, are looking to build a commercial communications relay spacecraft and service at the moon. So if you're at the moon with your lander at the lunar surface and you want to talk to home, you can do it via their communications satellite, which is at the moon, and the ground stations there, big dishes that they'll be using to receive communications at the lunar surface. And so one of the things we're doing in ESA is we're working with those companies and with others to understand how can we in ESA help them to make their commercial business at the moon work, with a view to making sure that Europe is a participant in this future commercial space exploration, and to see how we as an agency can support them in realizing their dreams. We're also working with Roscosmos on a very important mission called Lunar 27. And we have two contributions we're making to Lunar 27. Lunar 27 is a mission which will go to the south polar region of the moon, somewhere we expect to find this cold trap water, ice, and another chemistry. And one of the contributions is something called Pilot. Pilot is a precision landing and hazard avoidance system, something which you can use on a lander to make sure you land with very high precision at the place you want to go. And once there, we're providing a package called Prospect. Now, Prospect is a package for understanding resources. It will drill into the surface with the drill you see here. This is an artist's impression of Prospect on the Lunar 27 lander. It will drill beneath the surface to a meter or more. It will take samples from beneath the surface, extract them, and then pass them to the grey box you see here, which is a very complex chemical laboratory. In this chemical laboratory, the samples will be heated, and as they're heated, water, ice, and other chemistry that's trapped there will become liberated. It will come off. We will measure that to see what is there, how much there is, what its chemical composition is, to understand how it could be used and extracted in the future, but also to understand its origins and its evolution, and what it can tell us about the origins of life-enabling chemistry in the solar system. We can also then introduce other chemicals into the samples when they're very hot and perform some chemical reactions to understand how we might be able to take the oxygen out of these materials and produce metals and oxygen in the future. So it's a very important package in terms of both the resources and understanding resources at the moon and how we might use them, but also to understand the science of the moon and its history and what it can tell us about life on Earth and the chemistry of the inner solar system. And that's a mission that is planned for 2023, which we're working on now with our Russian colleagues. Another thing that we're working on, which is a very, very important project, is what's called the European Service Module for Orion and the Gateway. So Orion is the spacecraft which is being built by NASA in the USA. It will be the spacecraft that takes humans beyond low Earth orbit into deep space for the first time since Apollo. And Europe, ESA, is providing the European Service Module, which is the piece that you see on the back of the spacecraft just here, with the solar panels coming off of this X shape. And this contains the power and the propulsion elements and the light support elements for the Orion vehicle. And so the first one of these has now been delivered to NASA, is being introduced and integrated with the Orion vehicle, the first one ready for the first flight of Orion, what's called Exploration Mission 1. And we're now working to prepare the second service module for Exploration Mission 2, which will be the first Orion flight to include humans. So when Orion is operational, Orion will go to this place. This is the Gateway, and the Gateway is something which is in preparation with the international partnership that put together the International Space Station. So the International Space Station is an extraordinary place. It's the most complex thing that humanity has ever undertaken to do. It was done by a consortium of countries, including Europe through the European Space Agency, through NASA, the Russian Space Agency, Roscosmos, Japan through their agency JAXA, and the Canadian Space Agency CSA. And we're taking the model of how we work together as an international community to do that, and we're extending it into deep space to create a scenario, a place, a human-tended station in the vicinity of the moon, which will be the first place that humans go in deep space since Apollo, and will be the furthest outpost humanity has ever had in space. This will be the furthest that humans have ever been from Earth. Now, this is somewhere where we will learn to live and work away from Earth and away from the safety of low Earth orbit, where we learn to live away from Earth the furthest we've ever been. At the same time, it's somewhere we can do scientific research in the deep space environment, and it becomes a staging post to allow us to travel from orbit, from Earth to the gateway with the Orion vehicle, and then it becomes, if you like, a bit of a space port, and we can go to the lunar surface from the gateway using lunar landers and ascenders. So it becomes, if you like, a staging post for international exploration of the moon, and later beyond to Mars and elsewhere in the solar system. And this is something which we plan to start building with our international partners during the early 2020s. So looking beyond that, we talked about going to the surface and back again with humans, and we want to start building that capability to have humans living and working at the lunar surface. And so we're working again with international partners, in particular here with the Japanese Space Agency, JAXA, and the Canadian Space Agency, CSA, also with our partners, NASA in particular, about the gateway and the interface with that, on a mission which would be a human exploration precursor mission. So this would be a robotic mission to land at the lunar surface, to drive with a mobile rover, a robotic rover, around the lunar surface, to perform scientific experiments, to choose important scientific samples, and then to bring them back from the lunar surface to the gateway using an ascender that you see on the top of the image here, and then from the gateway to bring them back to the Earth with the astronauts on Apollo. That's something that we would plan to do during the second half of the 2020s. Working with our international partners, and through this mission to test and prepare the technologies that we would use to get to the lunar surface in the future. So this whole scenario looks a little bit different from Apollo, and one of the reasons for that is it's done in international partnership. It's also planned to be done in a sustainable way, so a way that is within the cost constraints, the budget constraints that exist in the present day, that use the technologies that we have in the present day, and prepare to do this in a way which has long-term sustainability. So Apollo was the most extraordinary program, but it ended. The intention is that human exploration of the moon and of space should not end. It should be something that continues, that grows and increments in a way where we learn with each step of the way, and we build on the things that have come before to create a long-term sustainable future for international space exploration. And so internationally, there is agreement that the moon will be the next destination for humans. And so we're also now working with international partners around the world, in particular through something called the International Space Exploration Coordination Group, which is ISEG-G, which is a meeting point of many different space agencies to discuss our plans together for the future of space exploration. And we're now discussing with partners about how we get humans to the future, building on these building blocks that we're establishing during the 2020s. And so this is something which is produced by this group of agencies, ISEG-G. It's called the Global Exploration Roadmap, and you can Google that, you can look it up, and you can find it, you can download it. It's a document which is produced by this group, ISEG-G, which explains overall what globally are the strategic plans of the different space agencies in the world, what do they want to do, and how do they combine to create a common vision, a common roadmap of what we expect to happen over the coming decades. And this figure, which you'll find in that document, if you choose to find it, explains, I think, a bit about what everyone thinks is going to happen. So on the bottom left, you find the Earth and low Earth orbit, where the space station exists today. And in low Earth orbit, the space station will continue for some time yet. At some point, the space station will come to an end, but we see future platforms coming. So the Chinese will plan to have a space station assembled during the 2020s. And then future platforms could include commercial platforms provided by commercial suppliers, where agencies and others could go on a commercial basis to perform scientific research, which follows and builds on the important work that's going on the space station today. At the same time, we travel for the first time to deep space. So with Orion and the Space Launch System, or SLS, which is being developed in the US. We would travel into deep space and start to assemble this deep space gateway, this staging post in the lunar vicinity. From the deep space gateway, we would develop the capabilities to get down to the lunar surface and initiate a human lunar surface exploration, supported by the gateway, and that should go off. You see that there's an arrow that goes off to the right there, as to indicate that this is not something that should end. This should be a sustained and sustainable human surface exploration campaign. So at the present time, we see robotic lunar missions traveling to perform resource utilization testing, to understand how we could use resources, what are the environment, to test technologies ready for these human missions that are to follow and to deliver science. And that's something you're starting to see now with all these missions that are coming from various different countries and different players around the world. And then from in the further future, we would see the beginnings of an architecture for exploration of Mars. And so we have a Mars sample return campaign, which would take place during the 2020s, which have been planned with the eventual purpose of having humans on the Martian surface as a common objective that is shared by all of the space agencies in the world, pretty much, I think, as something which would happen later in the next decades, after this initial period of human surface exploration of the moon. And perhaps at some point in the future, we will see the Moon Village. So the Moon Village is a vision of a shared habitation, a shared activity at the lunar surface with different users, different uses, different players, different suppliers, different needs being met by different actors, all at the lunar surface in a shared, cooperative and interactive way. And this is perhaps where lunar exploration will be heading over the coming decades. And we in ESA are working to create the partnerships, both international and commercial, and with the science community and with others, to make this a reality for the coming decades. So now I'd like to just sit back. I'd like to show you something as just kind of summarize a little bit of what I've said. Put it back. Let's start the movie. There we go. Thanks. So the 1960s and 70s were an incredible era for space exploration. At the Ranger missions from the United States, which took close-up images of the moon before impacting into the surface. And NASA's Surveyor missions demonstrated a controlled, soft landing at the surface of the moon and tested the properties of lunar soil to prepare for future human missions. A series of Soviet landers and rovers visited a number of locations, performing scientific investigations, driving across the surface, and returning samples to Earth. But the pinnacle of this period of exploration was Apollo and the arrival of humans at the surface of another solar system body for the first and the only time in history. Looking back now, we see that only a tiny fraction of the moon's surface has been explored, all on the side of the moon that faces the Earth and in a region close to the equator. We've also discovered that all of the samples that we've returned to Earth are from an unusual region with a complex and exotic chemistry of potassium, phosphor, and rare earth elements such as thorium. The vast majority of the moon has yet to be explored, including the entire far side. One thing we can say for certain is that if you want to understand the moon, then we need to go back there. Now, after decades of waiting, an armada of missions from around the world, including ESA's Smart 1, have returned to explore the moon from orbit. Looking down from above, these missions are providing a wealth of new data, bringing a new understanding and raising new questions. They are giving us a global insight and preparing for the next wave of missions to the surface, beginning with China's Chang'e 3 and Chang'e 4. And the next wave of missions to the lunar surface, where might they go? Well, the next destination will be unlike anywhere we have been before: the extreme and alien landscape of the lunar South Pole. Here, we find areas of permanent darkness and extreme cold, where water ice and other chemicals can become trapped. And as we come up from these lowlands, we see towering peaks basking in near constant light. On these polar mountains, the sun rarely sets below the horizon, providing the potential for near continuous solar power and a spectacular view over the rugged and cratered landscape below. In 2009, the L-Cross mission blasted water and other chemicals out of a permanently dark crater in the South Pole region, allowing it to be observed by nearby spacecraft for the very first time. We also now know that there are nearby locations with similar cold conditions. Is there water here too? If so, how much? Where did it come from? And what can it teach us about the origins of water and life-forming chemistry on Earth? Now, this water may have been delivered by comets and asteroids, impacting into the surface over billions of years. It may even have been created at the surface of the moon. We now know that protons thrown out by the sun in the solar wind arrive at the lunar surface. Here, they react with oxygen in minerals to create a thin layer of water. These water molecules can be lifted by the sun's heat before falling again to the surface. And over time, these particles may move to the polar regions where they are trapped by the cold conditions. And as we stand at the pole, with the Earth in view, we can point our antennas to the sky to search for faint signals from deep out in space. But radio noise from the Earth is too loud and blocks out many cosmic radio sources. But as we move over the horizon, the Earth sets out of view. The noise disappears and a new kind of radio sky emerges. We see our galaxy and the planets as never before. And beyond, a quiet radio hum, a signal from the cosmic dark ages more than 13 billion years ago, when the first cosmic structures were formed. And now, the moon as we see it today, scarred by craters over millions of years. And the first and the oldest of these, the South Pole Aitken Basin, formed by a powerful impact around 4 billion years ago. Many believe that its formation marks the start of a dramatic period of bombardment onto the Earth and the Moon, an era called the Cataclysm. This era is recorded on the Moon's scarred surface, and its end coincides with the appearance of the earliest observed traces of life on Earth. In the coming years, we will see explorers at the lunar poles, exploiting the extended sunlight for power and performing research to benefit life on Earth and to understand our place in the universe. This will begin with small robotic missions to understand the environment and prove new technologies to pave the way for the future. We will then move on to increasingly ambitious missions with humans and robots working together, learning to live and work at the surface and performing new and important scientific research. This new exploration will be achieved not in competition, as in the past, but through peaceful international cooperation. Eventually, we will see a sustained infrastructure for research and exploration, where humans will live and work for prolonged periods. Here, we will put into practice the lessons of years on the International Space Station to establish a facility akin to those we see in Antarctica today. In the future, the moon can become a place where the nations of the world can come together to understand our common origins, to build a common future, and to share a common journey beyond, a place where we can learn to move onwards into the solar system. And perhaps, in the future, at a sun-bathed peak at the lunar South Pole at the edge of a crater, we will learn to access and utilize resources from deep below in the dark. Zooming in closer and closer, we see water ice molecules trapped in the cold, a source of hydrogen and oxygen, essential for maintaining human life and for rocket fuel, fuel to propel us further into the solar system and to the next destination of our journey into the cosmos. Okay. So we asked you what exploration was. Let's see what you said. Okay, that's interesting. So science is very important to everybody. Astronauts, not so important. Interesting. The unknown, quite important. And future possibilities for humanity. Where are we going next? And of course, technology and danger and risk. And I'm glad that not many people said something else. That means I didn't miss too much. So thank you for that. So thank you for telling us that. So now you've told us what you think exploration is. I'd like to tell you what I think exploration is. No, I think exploration is a story. And it's a story about people. It's a story about the individuals. It's the story of Neil Armstrong. It's the story of Gagarin. It's the story of the people who are famous, people who go there, the astronauts that travel to those places. It's the story of the characters that come out of these things, the people that we remember. It's a story about how we are better together. So this is one of my favorite images. There's lots of versions of this, but this is an image where you see the moon, and hopefully just in the top corner there, you can see the International Space Station flying in front of the moon. Now, the International Space Station is the only place I can think of in the world today where Europe, the United States, Japan, Canada, and Russia are working together in a place of extraordinary complexity that was built together in cooperation by all these countries, where we live and work together every day, doing the incredible in peace as a standard way of working and in harmony together. And the fact that we can do that in space gives me hope on Earth. We are better together, and exploration shows us how we can do that. It's a story about human creativity and ingenuity. It's a story about the things that we as a species can do when we put our minds to it. We can land on comets, we can land on Mars, we can fly above the rings of Saturn, we can visit the outer reaches of our solar system, we can explore the moon, and we can understand there, we can go, we can live and work there, and more about ourselves. So we as a species can do the incredible, and exploration shows us exactly what we are capable of. It's a story about where we all come from and about our place in the universe. It's about what it means to be human, what it is to be on this little island of blue in a sea of emptiness, what it is to be these little things in this giant cosmos. It's about the history, our origins, and where we came from. It's about the chemistry that makes us up and where it comes from. It's about understanding all of these things and its context in the vastness of space. It's a story about our future and where we're going next. About our species, where do we go next? What are the possibilities? What can we accomplish? What will our children and our children's children see? What will they do? What will they accomplish? Exploration gives us some insight into that and prepares the way. I also think it's a story that everyone is in. So during Apollo, everybody in the world somehow participated in Apollo. A huge fraction of the world's population observed Apollo in real time as it was happening, as Neil Armstrong took those first steps onto the lunar surface. And that was possible through a new technology called television. Now, as we look to the exploration of the coming decade and beyond, how much more so with the technologies we have now, to the technologies that are allowing me to talk to you today, the technologies that are allowing you to participate in the Mentimeter and tell us what you think from wherever you are in the world, the technologies we use on social media, and technologies that we cannot even imagine today that are going to exist in 5, 10, 20 years' time. So I think exploration in the future will not be something we watch, it will be something we participate in. And if that's true, then exploration is your story. And I hope you enjoy it. Thank you.
Well, just the two of us clapping. Thank you, James. That was extremely inspirational and full of information. I was following the chat, and I think I have like a general question that people were asking. That is about the story of the Moon Village and how are we building this Moon Village? What type of structures are we using? What type of materials are we going to use on the Moon? And also, what is the impact that we will have when we do so?
Okay. So the Moon Village is a vision that is about the coming together of different people at the lunar surface. So the Moon Village is not in itself a structure or a base. It's more a social structure. So in a village, the way our Director General talks about it is in a village, you have a shopkeeper, you have different people in the village who bring different things to a community to make that community function. And so the Moon Village is more about the coming together of different actors, different countries, the public sector, the private sector, scientists and others all coming together with different capabilities to create a community at the lunar surface. Now that's going to require transportation, it's going to require mobility, it's going to require power, it's going to require construction, material, all sorts of things. And so that's how the Moon Village should be understood rather than being a base as such. That said, we do have activities. We are looking at how would you build structures at the moon. And so we're looking at new technologies where you could take the lunar regolith, this material that I see there, and use that as a material for construction. Maybe you create bricks out of this, maybe you could do other things. And that's one way you could build some of the structures, particularly for radiation protection, for protection from the heat outside and the cold outside, so thermal insulation. But also you can create things like landing pads if you can sinter this to make kind of a hard surface and other kinds of things. So we're investigating those things at the moment. Most of our work today is, I would say, on establishing some of the early stages of exploration. So how do we get there? What are the technologies? What are the partnerships that we need to build? What are some of the basic technologies that we would want for the future? And so the next steps will be about getting robots to the lunar surface, using those robots to do science and technology, to understand how we can use some of the resources locally, with a view to later on, once we've at the surface working with humans, to then start really thinking seriously about how we take that to the next step, whatever that step will be.
Okay, I think you have one more question for them, right, with the Mentimeter?
Ah, yes. So over my shoulder, you also see this. So just while we're speaking, you can add your ideas here about why we should explore. Actually, this is very interesting for us, but also a way to maybe record some of your own thoughts about what exploration's about and why we should explore. So there's about a 10-second delay, I think. So about 10 seconds after you put the thing into your phone or your computer, you might see it come up here.
Okay. So I think we are done. Thank you very much for joining us and giving us this presentation. So the next webinar will be next Monday, so very soon, and it will be at the same time. And we'll be joined by Mark, and he will present us how to do a 3D design of a future Moon Village. Why not? So thank you very much for joining us today, and I'll see you on Monday. Thanks.